Hi everyone, my name is Jonah Turner, as I was introduced. I'm a PhD student from Loughborough University. So what do a team of robots and a travelling salesman have in common? So my research is actually on task allocation for teams of robots in search and rescue missions. So that involves robots, a disaster, and we're going to come to the travelling salesman afterwards and find out how that all adds up to me hopefully getting a PhD. So yeah, I want to take you on a journey, and I hope by the end of this talk you'll have a good idea of why teams of robots are useful in search and rescue missions, what are the challenges of coordinating them, and how that relates to other applications, and especially that travelling salesman. And more importantly, what my research is about, so how to get a team of robots to coordinate a plan in a rescue scenario between themselves, and what my contribution to the research is. So we're going to start with why robots in search and rescue missions. So in a disaster scenario, you can have all kinds of hazards, like biohazards, nuclear hazards, extreme heat, all kinds of problems that humans wouldn't be able to operate in. So robots are useful in that environment because if there's a valve that needs turning, a robot can do that. Robots are also useful, say if you've had an earthquake and you need to inspect the structural integrity of a building, you can send the drone up with a camera and collect data. It's all very good. But so it illustrates the benefits of a robot, robots versus human. Robot's going to win in that situation. How about one single robot that can do everything, or many robots which aren't as clever, but are specialized in certain aspects of applications? So one robot's cool, but in disaster scenarios, you can have all kinds of unpredictable situations and problems. So if there's a fault or something unexpected happens, you've got one robot, that's game over. But if you've got many robots, it's much more robust to failures. And if you're wondering what kind of robots have been built in the past few years, here we have a nice variety. We've got the fly, we've got aerial robots, ground robots, underwater robots. Basically, so we've been developing robots that can tackle all kinds of terrain that would be useful in search and rescue scenarios. But when you've got many robots, you have to think about how you're going to coordinate them, how you're going to get them to figure out what they're supposed to do. So you have two main options, which is a centralized system. So each robot communicates with a central server. And that's good because the central server has all the information and can make a very well-informed plan and feed it back to the robots. There are some issues with this, such as the robots have to stay within the range of the server, which means if it's over a large area, it could limit the search area. Also, as the number of robots increases, that could put a very heavy burden on the server. But also, if there is a problem and the server goes down, then that's it. Full mission's over. The other option is a distributed system. So in this scenario, none of the robots have all of the information, but they have a planner on each of them, and they all contribute to coming up with an overall plan by communicating with each other. And this is good because if there's a problem, then the rest of them can still continue and keep communicating and coming up with plans. And this looks a bit like this in a more realistic scenario. So you might have aerial vehicles communicating with ground vehicles in between buildings, that kind of thing. So I hope at this point I've convinced you that in a rescue situation, a team of distributed robots is the way to go. And that's great because that's what my research is actually on. So what's the challenge? Okay, so we've got a number of survivors, they've got a deadline. So it could have been a tsunami and they need rescuing. And then we've got limited resources. So we've got a bunch of robots. They've also got fuel limits. So we want to get those robots to coordinate between each other a plan that can rescue as many survivors as possible in the least amount of time. Now, if there are any mathematicians among you, usually what they tell me when I explain them what I'm doing, they say, "Oh, that sounds like the traveling salesman problem." And yes. So in fact, the traveling salesman problem is a mathematical problem that was formalized many, many years ago. And the idea is you've got a number of cities, and you've got a traveling salesman. Between those cities is an associated cost, so it could be a distance or the time it takes to travel between each city. And the goal is to find the route that the traveling salesman can travel that minimizes the cost. So either the least amount of time or the least fuel cost. So that's very similar to what our problem is, because we've got robots and people to rescue, and we've got to minimize the cost. In this case, we want to minimize the time that's taken in total. It is slightly different because we've got a number of traveling salesmen. But this is important because by sort of abstracting the problem, then you can notice all the other applications that are trying to solve the same problem. So for example, we're trying to solve the same problem as maybe a taxi company would be if they have impatient customers, and the time limit on the taxis could be working hours, for example. And then you've got a supermarket that's trying to deliver perishable goods to hungry customers. So as you see, if you solve the problem in one area, it can actually carry over to many other areas. So now I've given you a background. Now I want to give you a kind of general idea about how task allocation might work. So MIT developed an algorithm called the consensus-based bundle algorithm, and that's what my research is based on. It's very simple. It runs on two different phases. So you've got phase one, which is task inclusion. Each robot just takes the information of each task, which includes the location and the deadline, and adds it into their schedule using some sort of strategy. And then you've got the conflict resolution phase, where robots communicate which tasks they put into their schedule, and if any of them have picked the same tasks, they have to resolve the conflict, because you don't want the same two robots to do the same task. So what's already been done is to sort of minimize the time, is use a strategy that corresponds to that. So for example, which task is the robot going to add into its task next? Well, to minimize time, you would say the one it can reach earliest. And if you've got two robots that have got the same task, the one who gets to it earliest can keep it. And that's a very simple sort of strategy. So if you've got one task and one robot, we've got Alan, who's going to help us out here. You don't really need any rules. You just select that task. If you can reach it in time, great. So that number there corresponds to the time units that it takes for Alan to reach this happy survivor. So if you've got two tasks, you've got A and B, you need rescuing. Alan is going to look at how long it takes to get to each. He's going to pick the one he can get to earliest. And then he's going to see if he can get to the other one as well. So first go to B, then A, doesn't work. Can't get to A in time if he does that. But if he goes to A and then B, he can get to B in 8 time units. Great. So now demonstrating the conflict resolution phase. We've got Alan and Bill, and they both want to save this person. But Alan can get there first. So when they communicate, they realize, okay, Alan's got a smaller number there. So Alan keeps it. That's great. And then we can build on this problem, get a bit more complicated, give you a bit more of an idea of how it works. So Alan and Bill fighting over 2 tasks. So they're both going to pick the first task, the closest task first, and then the further task to expand their task schedule. When they communicate, they'll resolve the conflict by giving it to Alan, because he's got lower numbers for each of them. Then Bill's going to keep trying to include tasks. Wouldn't bother with A, because Bill can't improve on Alan's 2 with a 3, but can improve on 5 with a 4. And then they communicate, resolve the conflict there. And that's basically, so it doesn't matter if you didn't follow it completely, but hopefully I've given you an idea that the rules involved are very simple and you come up with a good task allocation. Obviously this is a very simple scenario, so if we make it a bit more complicated, here I want to demonstrate to you what the limitations of this method might be. So just using the same rules I just explained, we would go through the same process. Alan's going to pick the closest one and then see which other ones it can get to. Bill's going to do the same, and Carl's going to do the same. So we've got 2 conflicts there. They communicate, resolve the conflicts. Alan keeps it because he can get to it to see soonest. And then Bill and Carl resolve their conflict. And then after that, they can't improve on this allocation. So using very simple steps, you can reach this configuration, which is great, except there's one task that hasn't been allocated. So if you're that person there, you might not really be happy with that. So this is where my research comes in. I wanted to figure out a way that would enable the robots to just very efficiently reconfigure their task lists without having to go through the whole process again. But only if such a task exists, because if you've only got B to E, then that's fine. If there are many, many more tasks, you don't want to go through the whole thing again, because that will take a lot of time. So I came up with a simple rule to add to that, to just change the scoring strategy. So rather than basing it on time, it's a rule that says if you can get to another task instead of the one you're going to, then the cost of the task in your schedule is going to be slightly less than the one that you're potentially replacing it with. Now, it doesn't matter if that didn't make sense. It's just a simple rule that I'm replacing the time to get there with. So I want to kind of simulate what happens with that rule from the configuration that we start with, and to see if that helps us to get to task A being allocated. So what I'm doing here is Alan is checking if Alan doesn't go to B, can it go to another task? And it's going to check if it can get to A. We've given A a cost of 20 as an arbitrary number, and Alan can reach A. So we give B a cost of 10, which is slightly less. Then they communicate. Bill does something similar. It gives D a cost of 5, which is slightly less than B. And then Carl can now get to D at a cost that's lower than Bill's. So that's useful, because then when they communicate, Bill releases the task and then can go to task B. Alan then loses the task and is free to go to task A. Now, I know that's kind of a bit difficult to follow, but I hope at the very least what I've given you is a sort of overview of what it looks like, and it doesn't involve too much. I mean, if we went through it, much slower, then I think it would be quite easy to follow. But this is great, because now all the tasks are allocated, which means all the survivors get rescued, which is very important. So here are 2 lovely graphs. What we did is we ran lots of simulations, starting from the original algorithm. We wanted to see how well this new method could improve on a solution. So we ran simulations many times. In the first graph, we've got how many times the new method could improve on the original solution. And in the second one, by how much. So in the first one, we see what it shows is we've got 2 different ratios, and we've got a number of different vehicles. But basically, when there's a high task to vehicle ratio, nearly 100% of the simulations, the new method improved the original solution. And this occurred by up to 20%, which is quite a significant increase. If you're in a search and rescue scenario, that you could, from 35 survivors being rescued to 42, for example. I mean, that's quite a big difference, especially if you're one of the 7 that gets rescued. You'd be very happy with that. Yeah, so that's essentially my research. I just want to summarize what we went over. Yeah, so distributed task allocation is a challenge across many fields, including search and rescue. The question in the title, the answer is the team of robots and a traveling salesman both have a complex problem to solve. And what we did is we introduced a new cost that increased significantly the number of allocated tasks. So I hope this has been fun for you. It's been fun for me, and yeah, that's it.